Okay, so you've had a couple minutes to do these here. Hopefully you noticed that you were dealing with the same function on all three in each column here. So what's the integral of 2 cosine? 2 sine. All right, so that's the case for all of these. 2 sine x, 2 sine x, 2 sine x. Okay, I'll get it here. Unfreeze it so you can see. There we go. All right, but you're just integrating it on different intervals for these, okay? So we have 0 to pi over 2. We have negative pi over 2 to 0. We have negative pi over 2 to pi over 2. Now, what is sine of pi over 2? 1. What's sine of a negative pi over 2? Okay, so this is going to be 2 times 1 minus a negative 1. So 2 times 2 is 4. Okay? Now, what's sine of 0? 0 minus, we still have the negative pi over 2, so that's still minus a negative 1. So this is 2. Okay? And then we have sine of pi over 2, we already said was 1.
That is still 2.
Yeah, it's going to be 1 minus 0, so this also equals 2. Okay? Now, 2 cosine of x. You may be able to visualize this, but let me quickly sketch 2 cosine of x, where a cosine starts at the top, so it's going to be up here at 0, 2. And then we're going to have something that looks like this on this side, same thing on this. How would you describe that function? Okay. How else? There is symmetry across the y-axis. Okay. Do you guys remember the term for functions that were symmetrical across the y-axis? Yeah, those are even functions. Okay. Those are even functions. Yeah. So here you'll notice the area that we got from negative pi over 2 to 0 was the same as the area we got from 0 to pi over 2. That's because of the symmetry. Okay? And that gives us what we see right here. Okay? If f is an even function, then the integral from negative a to a, notice you have to have opposites as the ends of your interval. But the integral from negative a to a of f of x dx is going to be 2 times the integral from 0 to a. Okay? As you can see here, all right, this is going to be the same area as this. So we could just find this part and double it. That's what this is saying. Okay? Make sense? Okay. Now, let's go back here to the second one. Okay, we had this x cubed. So the integral of x cubed is?
X to the 4th over 4.
Yeah, x to the 4th over 4. So that's the case for all of these. We're just evaluating it from negative 2 to 2, and then we're evaluating it from negative 2 to 0, and we're evaluating it from 0 to 2. Okay? So if we plug in 2, what do we get? 4. If we plug in negative 2, what do we get? 4. So that's going to be 0. Okay? If we plug in 0, what do we get?
0.
Alright, wake up. 0 minus 4 again. That's negative 4. If we, or I'm sorry, yeah, that's negative 4. If we plug in 2, we get 4 minus 0, and that is positive 4. Okay? So you'll notice here, in this case, the integral from negative 2 to 0 is the opposite of the integral from 0 to 2. Alright? And that, if you remember what this function looks like, the cubic parent function, we're at negative 2, negative 8. Okay? So this area right here is the negative 4. Whereas this is the point 2, we go to 8. Wait, sorry. I colored in the wrong side over here. That's not negative 4. This is negative 4. Okay? And over here, this is positive 4. Okay? And you'll notice those cancel out. Now, how would you describe this function? What do you notice about, how would you describe this function? Okay, yeah, this is symmetry across the origin. Or we could say about the origin, or around the origin. In other words, if you use the origin as kind of your rotational point, and you rotate it 180 degrees, it'll look identical to itself, okay? So if you were to rotate this 180 degrees, it would be identical, okay? Another way of thinking of it is you reflect it across the x-axis and the y-axis, and you get that rotation. So it's symmetry around the origin, okay? So, now, what's the name for that kind of a function? It's odd, okay? We just talked about even. Those are the odd functions. There's symmetry about the origin. And you'll notice here the relationship that we can see is that when we have that and we're taking the integral on an interval that has opposites for the ends, so from negative a to a, then the areas will actually cancel each other out, and the total area would be 0. Okay? So the area there is 0. Okay? Any questions? Comments? Anything?
How will you test us on this?
These are just relationships. The more of these kinds of relationships you see, the simpler you might be able to solve a problem. It's not that maybe you won't be able to solve a problem in a certain case, but it'll be a lot easier in a certain case. Okay?
How are we going to look at if they are even or odd except for this?
Well, that's where your understanding of functions from back in pre-calculus, we talked about even and odd functions. Remember, even functions are functions where if you plug in a negative x, it's going to be the same thing as the original function. And an odd function was when you plug in negative x, you get negative f of x. Okay? So that was the odd function. So let's take a quick look at an example here. We're going to do the integral from negative pi over 2 to pi over 2 of this function here. And you're given the graph of what this looks like. It's sine cubed x times cosine plus sine x times cosine x. We need to do something with this so that we can integrate it, okay? Now, looking at this here, what do you recognize?
Odd.
It looks odd, okay? Now,
So you simply do from, it's going to be 0 because it's going to cancel.
should we test?
No.
I mean, you don't have to, but
Let's double check, okay? Let's double check. I mean, we can see the graph here, all right? But let's double check. Let's say we aren't given the graph. If I plug in sine cubed of negative x times cosine of negative x plus sine of negative x times cosine of negative x, okay? Let's simplify these based on our even and odd identities from last year, okay? Cosine itself is an even function. We just saw that earlier when we looked at 2 cosine of x. So if I have cosine of negative x, that's going to give me cosine of x. Good, Peter. Just cosine of x. All right? Now, how about sine? Is sine even, odd, or neither? What do we get when we do sine of negative x?
negative sine of x.
Yeah, that's going to be negative sine of x. Sine, remember, is like this. That's an odd function. Okay?
I took the example given with the what's it called? In the you try it at the beginning with the pi over 2 versus the negative pi over 2.
Yeah.
You would go with the 1, the negative 1.
Yeah. So that is going to simplify to negative sine x. This is going to simplify to negative sine x cubed, which is negative sine cubed x. Is that the opposite of what we had originally?
Yes, it is.
Yes. Therefore, it is odd. Okay, that equals a negative, I'll just put negative f of x. Alright? So this means it's odd. So what does that integral equal?
0.
It equals 0. Okay? Now, could you split this into 2 separate integrals? Do u substitution for both of them
You could.
and figure out what in the world that whole thing is?
Oh my
Sure.
god.
Sure. Do we want to? No, because it's going to come out to 0 anyways, right? So, this is answering Chloe's question. Am I going to specifically ask you to do that? Maybe not, but it certainly will save you a whole lot of work in cases where this takes place. Okay?
If a function is not even, so that is odd.
No, they don't. It's possible that a function isn't either one.
So what are we going to do?
In those ones, we would just have to do the integral.
How are we going? Yeah, but I don't think if there are any functions doesn't belong to either even or odd function.
Well, think about just a basic like a cubic equation like this. All right, that's a function, right? If I took that though and I flipped it across the x-axis, or I'm sorry, the y-axis, and I made it look like this, do I get the same thing?
No.
I didn't quite go high enough, but still. No, I don't. So it's not an even function. And if I were to take this and I were to rotate it around 180 degrees, that one's a little bit harder. It would look like this. Is that the same thing? No. Alright, so that one is not even or odd. And that's okay. Not every function is. Alright? This is just for cases where you do have an even or an odd function. So to summarize here, basically, here's what you need to take from this. If you see a case where your interval that you're using are opposites, think, is the function I'm working with even or odd? And to test, plug in a negative for x, see if it comes out the same. Or see if it comes out the opposite, and then you'll know if it's even or odd. If it comes out as something different, you know you're just going to have to take the integral as you normally would. Okay? Alright. So, that's it for the even or odd. I want to step back, though, and get back to integrating by substitution. And we're actually going to get beyond just the indefinite integrals. And today I want to look at definite integrals, okay? Definite integrals. Up to this point, every one of these we've done has been indefinite integral, so we always substituted x back in, or whatever we had u equal to, we substituted that back in, so that our answer was still in terms of x, okay? What we're going to look at here, though, is kind of a cool thing, and that is that you can change your variable, and rather than plugging u back in at the end, you can change the interval that you're integrating over to be in terms of u instead of x as well. Let me illustrate here with this one. We'll actually, and it's really just a difference of what you want to do at the end, okay? So, if I'm doing this one, what's u going to equal in this case?
X squared plus 1.
Good, x squared plus 1. U equals x squared plus 1. Alright? So du is what? 2x dx. Alright? So I almost have what I need for my du. I'm missing the 2. So I need to put the 2 in there.
And multiply by 1/2 on the outside.
Very good. And multiply by 1/2 on the outside. Okay? So now we have 1/2 integral of x squared plus 1 cubed times 2x dx. Alright? And that's from 0 to 1. Okay? Now, at this point, I will do the substitution, and I have 1/2 integral of u cubed du. Notice I'm not writing down the interval at this point, the upper and lower bounds, okay? I'm going to hold off on that till I get towards the end, alright? So at first here, I'm just thinking in terms of the antiderivative. So now I do 1/2 integral, or not integral, 1/2 times u to the 4th over 4, which is, of course, u to the 4th over 8. Now, here's the problem people run into. Problem number 1 is they will take the 0 and the 1 and they'll evaluate it at this point. Okay? However, the 0 and the 1 were not values of u, those were values of x. Those are x's. So, I need to do one of two things, okay? I can sub the x's back in. This is what we've been doing. So I would then say, okay, well this is x squared plus 1 to the 4th over 8. And now I'm going to evaluate that from 0 to 1. Okay? So 1 squared plus 1 is 2. I have 2 to the 4th over 8. Minus 0 squared is 0. So I have 1 to the 4th over 8. 1 to the 4th, not 14. Alright, so 2 to the 4th is 16 over 8 is 2. Minus 1/8. That's 1 7/8. Okay? The alternative. The alternative is what you see up here. Notice what they have done is they've changed the interval by plugging A and B into U and figuring out the values of U. Okay? So notice what I could do here. I'm going to, for x equals 0, U is going to equal 0 squared plus 1, that's 1. For x equals 1, U equals 1 squared plus 1, which is 2. So, coming back to where I was doing the integral before, I would actually be doing the integral from 1 to 2. Okay? Once I substitute U in, notice from 0 to 1 is going to change to be from 1 to 2. Alright? So right there and right there, those are U's. Okay? Then when I get here, I don't have to plug in the x squared plus 1 anymore. I can simply do U to the 4th over 4, or U to the 4th over 8, evaluated from 1 to 2. Okay?
Don't you have to close these parentheses when you write that down?
This, you'll see it written both ways if you want. Yeah, you can. I guess we've been writing it that way, so sure. Okay? Now, either way, notice what you're going to get. You're going to get 2 to the 4th over 8 minus 1 to the 4th over 8, which is, again, 1 7/8. You'll get the same answer either way.
So you don't even have to plug in x squared plus 1 in any moment?
You don't have to sub it back in as long as you convert your boundaries into boundaries that are values of U.
Oh.
You've got to use those upper and lower bounds
Not
that are values of U, not the originals in terms of X.
okay.
Okay? So, you can either sub the X's back in. Some people like that. They don't like messing with the boundaries or whatever. Other people like this. Change the bounds to be in terms of U, or to be values of U. Okay? So there you've seen it both ways. You may determine that, hey, in this case it seems easier if I just plug those in and change the boundaries. But on the next problem you might say, hey, I think it'll just be easier to plug the x's back in. It's totally up to you. Okay? Alright, so there I've highlighted where the 1 and the 2 came from. We're just changing variables completely. So the first kind where we did the U substitution, we were changing variables, but we had to change it back. at the end because our answer was just an indefinite integral and we wanted it in terms of x. In this case, with the definite integrals, we don't care about what it looks like in the middle. All we care about is that number at the end. So whether we change variables completely to u, like we did in the green, or whether we change it to x, but then change it to u and then change it back to x, either way, we'll get the same answer at the end, so we don't care which method you use. Okay? Alright, let's try another one here. Okay, here we have the integral from 0 to pi of sine of x plus cosine of 2x dx. Okay. What are we going to have to do to integrate this?
At the integral function.
Yeah. No, you're right. I mean, but how do we get the integral of the function?
Do we use the u? I don't think we are going to use the u.
Well, let's think about it here.
Let's use chain rule.
Let's plug in x and negative x, and oh wait, they're not the same.
Yeah, these aren't opposites, so we can't use the even-odd function.
Could you use the double angle identity? With the cosine?
We could make that what, like a 1 minus 2 sine squared x, if you want.
Why don't we just split it?
Yeah, I like that idea. Let's split it here, okay? Because then we can do the integral from 0 to pi of sine of x dx plus the integral from 0 to pi of cosine of 2x dx. Okay? Now, the first half here, that's a simple, what's the integral of sine? It's negative cosine. So I'm doing negative cosine of x evaluated from 0 to pi. Now let's go ahead and finish off this part. What's cosine of negative, or cosine of pi?
-1.
Yeah, so that's a negative 1. What's cosine of 0?
1.
Okay, so that's going to be negative 1 minus negative 1. Okay, got a lot of negatives in there to keep track of. Alright, so that's going to be 2 plus 2, or that's going to be 1 plus 1, which is 2. Alright, so now we just have to do this other half. Okay. Now the integral of cosine of 2x. Here's where the u substitution comes in. What is u?
2x.
It's 2x. So du is 2 dx. Alright. So I need a 2 here, which means I need a 1/2 here, right? Now, let's change the variable completely, okay? Because right now, I'm going to have 1/2 integral of cosine of u du. Okay? But if u is 2x, well, if x is 0, 2 times 0 is 0. If x is pi, 2 times pi is 2 pi. Okay? So instead of 2x, I have 2 times 0, I have 2 times pi. So we have 2 pi, and we have 0 as our new boundaries for the integral. Okay? And notice it's okay to only change the variable on the half that we're working with here. Okay? So now we have, what's the integral of cosine? Sine, alright? So we have 1/2 times the sine of u evaluated from 0 to 2 pi. What's sine of 2 pi? What sign of 0? 0. So this is 1/2 times 0. So the whole area here is just 2. Okay? That make sense? Okay? By the way, don't be afraid to use what you know about a function to help you find the integrals. This is where those of you who really know your stuff can help yourselves out. If I did the graph of cosine from 0 to 2 pi, that's 1 full period, right? I went a little too far. Okay, if I do 1 full period, what's the area?
0.
0, yeah. So it makes sense that we got 0 there, right?
Yeah.
So you can even save yourself a little bit of time if you're thinking in terms of the graphs. But again, you really got to know your stuff to make all those connections. But if you can make those connections, it really, really does help. Okay, you could see, oh wait, yeah. If I take the integral of 1 full period of a cosine function, or a sine function for that matter, the areas are going to cancel each other out. So it'll be 0. All right. So that's it. Wanted to look at that. We've been dealing with the changing variable with indefinite integrals. I wanted to show you both strategies for dealing with definite integrals. Either method is totally valid. Sometimes one method might be a little easier in the end than the other will, though. Okay? So it's totally up to you.